All right, class, let me try another video solution here. This is, again, from our relativity, number 19. And it says this. It says that Susan observes two light pulses to be emitted from the same location, but separated by 3 microseconds. All right, so we've got this one observer. I'll put an S for Susan. And then, of course, this other observer is Mark. Mark observes the emission of the same two pulses to be separated by 9 microseconds. Okay. Now, they don't say how far apart, if at all, Mark sees them. But the point is, Mark sees a different time than Susan. And so that means they're moving relative to each other. So I need one reference frame, which we often call the unprimed system, and another moving frame, or another system moving relative to it, and we'll call that the prime system. Now, let me take this as a moment to say we could pick Susan to be here or here, and then Mark has to be the other one. There is no right or wrong answer to say who's at rest and who's moving. That's why this is called relativity. They're all relative to each other. And it would be kind of fun to do it both ways. But let me just pick one way and stop there and maybe leave it for a challenge to you to switch Mark and Susan's reference point and then recalculate, and you're going to get the same thing. So to say who's at rest makes no sense. It's just to say one's moving relative to the other. And so we're just going to say that, okay, let's give this Susan, since I did this one first, and so over here is M for Mark. So Mark's in the prime reference system, and Susan is in the unprimed system. And hopefully the big lesson you got out of this chapter is that positions and times can vary or change. They're not absolute. It depends who's doing the watching. And so what Susan sees and what Mark sees are not the same positions. They're not the same time frame. And we know that already because they say this. And so they say that there is two flashes. What is it? 2 pulses or something? Susan drew 2 light pulses. Okay, so 2 flashes of light that are actually at the same location. I'll call it delta x is 0 between these 2 flashes. You might label this as x2 minus x1, where x1 is the position of the first flash and x2 is the position of the second flash. And according to this information, they are emitted from the same location. And so, maybe this is light on the front of a train and the back of a train, and as the train goes by, right as it gets at this spot, it makes a flash. A little bit later, it makes another flash. And from Susan's perspective, those are at the same location. Now, we can pick our origin anywhere we want, so why don't we pick the original flash as viewed by Susan to be the origin for Susan. So let's call x1 equals to 0. And then, of course, since the change in position is 0, that gives us the second flash of light also occurs at 0. So again, if this is a train, maybe my pin is the train, here's the front of the train, here's the back of the train. Train gets kind of in the middle of the screen, flash. 3 microseconds later, the back of the train gets here, flash. But both of these flashes occur at the same place. Now, we can do the same thing about time. The time between the 2 events for Susan is 3 microseconds. And what I guess we mean by that is time 2 minus time 1 is 3 microseconds. So again, just like we can pick the origin anywhere we want, we can pick our starting time anywhere we want. So let's use this as our pick. And so that very first light, so here's the front of the train, flash. Let's call that time equals to 0 for Susan, and let's call that a position 0 for Susan. And then so the second flash occurs then at time 3 microseconds. Okay? So these are the position of the two flashes, 0, 0. And these are the time frame of the two flashes. The first one, and then 3 microseconds later, the second one. All right, so Mark, though, is in a moving reference frame. And we can go through the same logic. We could say, well, there is a delta x. There is a distance between those two flashes. So again, kind of like this train, if it's coming by, from Susan's perspective, which would be your camera's perspective, it would go flash, then the back of the train flash, and you'd say they happened at the same spot. But if Mark is moving, so here's Mark, maybe it looks something like this, where the train is moving along and Mark comes in really fast, and it occurs right when Mark's sitting at the front of this spaceship, then sees this flash, and so that's flash number 1. But then, by the time flash number 2 takes place, Mark is way down here, and from Mark's perspective, the flash is not occurring at the same location, but way behind him, some negative location, at least in my picture. I don't know, this problem's going to come out to be negative. But here's my point. There's an x2 and an x1 also. Now, they don't say in this problem how far apart on that. In fact, that is part B of this problem. It says, according to Mark, what is the separation? So this is actually what we will be hunting for in part B of this problem. How far apart are they? But let me do the same kind of thing. I'm sorry, these are primes. Okay, let me call x1 prime then equal to 0. Again, I can call the origin 0 anywhere I want. So wherever Mark sees that first flash, let's call that 0. What we don't know then is where that second flash occurs to Mark. It could come out to be 0, highly unlikely because they have different times. They have to have different spacing. So not is it just highly unlikely, it's impossible. Okay, so this is going to be some number because Mark is moving relative to the camera here. This black one here is moving Mark. Now, we could do the same thing with the delta t, which, again, they did give us a time frame. They say it is 9 microseconds. Now, remember, moving clocks run slow. So the time between the flash is a little bit longer as seen from Mark. See, there's only 3. This is 3 times longer. And so that's going to be my gamma factor, that factor of 3. That right there can actually let me solve this for the speed between them. But let me just keep going through the notation, because then this, oh, I forgot a prime again. So this would be T2 prime minus T1 prime. And again, we can call this first flash, time number 1, anything we want. So these are our definitions. And so again, that very first flash, when it's seen by Susan, that's 0 position at 0 time in her coordinate system. And again, Mark sees that first flash and defines that to be his origin and his time frame of 0. And of course, if you define T1 prime equaling to 0, that makes T2 prime equaling to 9 microseconds. Okay. And so part A in this question is, how fast is Mark moving relative to Susan? Well, let me grab the textbook here. And let me flip back to the end of the chapter 39. And there's a little summary page here. And you'll see that they have a Lorentz transformation here saying, okay, what is the mathematical connection between position and time? And the unprimed system is what Susan sees, and the prime system is what Mark sees, okay? And the derivation of this is a pretty long explanation, so I thought for this problem I better just jump right to the equation here. But it looks like we might want to solve this for, let's see, we know, well, the ones would be kind of boring because we would put in 0, 0 for the ones and get a 1, get a 0 there for the time 1. But this might be the one for time 2. So let me copy this formula down, and I should take a moment and think about that. Is that? Yeah, I think that's the better approach. All right, so let me move the textbook out of the way and then write down what it's saying. So it's saying the time as seen by the prime system, which in this case would be Mark, would be equal to this gamma factor. That's where the speed between the two is going to come into play, times the time as seen by the unprimed system, so this would be Susan, minus v, so there's again the velocity between the two I'm looking for, over c squared over the position as seen by Susan, the unprimed. So these are the position and time as seen by Susan. This would give you the time as seen by Mark. This is the transformation from one person's view to another person's view. Now, if we apply that to number 2, so second position, second time, will give me the second time as seen by Mark. We know this is a 9 microseconds. I should put the units. Here's the gamma factor. We know time number 2 is 3 microseconds. And we know position number 2 is 0. And so moving this 3 over to here, we have a gamma factor of 3, which is what I said earlier, what this was going to come out to be. Okay. Now, gamma has a square root in it, so let me square everything, because then this would become 1 over 1 minus v squared over c squared. And so when I cross multiply, this becomes 9 minus 9v squared over c squared equals to 1. Moving the 9v squared over c squared to the right and the 1 to the left is going to give me an 8. And so running through the math here now, I would have this 8 divided by a 9, and then taking the square root of that is v over c, and then moving the c over gives me 0.943c. So there is the speed. So you got to get going pretty close, almost 95% the speed of light before things change by a factor of 3, which is a big factor. I mean, can you imagine things looking 3 times smaller or time taking 3 times longer? So it's a huge speed, and it's a world we don't really understand because we don't live in this world of this massive speed. Okay, so now that we know the speed between Susan and Mark, we can ask the second part of this, which really is the x2. And maybe to answer that, I'll just bring the textbook back in the screen here. So there it is. There's the transformation. There's how we get the position in the prime system. So that's going to be Mark relative to, and then here's the gamma factor, and then this is the position of Susan, the unprimed system. So knowing the position as Susan sees it, we can get the position as Mark sees it. So this is a gamma. This is then an x minus a vt. Now, if we say this is the position 2, then if I'm saying that right. So if this is position 2, yeah, from what Susan sees, this would be what Mark. So that'd be a prime. That's what I'm looking for. Okay, so that's what I want to find, x2 prime. All right, well, this gamma factor we did a moment ago, that was a factor of 3. And we talked about position of Susan. So her second position, or the second flash, was also at position 0. We've got a speed of 0.943 c. And then we've got this time number 2, which is the 3 microseconds. So where is the position of the next flash? All right. So why don't I take the 0.943 first, then times c, the speed of light, 3 times 10 to the 8th, times the 3 microseconds. So those are those 3 factors together. Then multiply it by the gamma factor, and that is 2,546 meters. And I think that's it. All right. We got them both. Take care.